Alright, let's talk about relative motion in 2 dimensions and in 1 dimension. So in your book, you have 1-dimensional motion in 4-6 and 2-dimensional motion in 4-7, but we're going to put them together and make some sense of this. This is a phenomenon you observe all the time. If a car is passing you, let's say you're going 60 miles an hour on the freeway and a car passes you at 70, well, that car has a relative velocity of 10 miles per hour with respect to you, right? Well, we're going to build up on that. So let's just start with position. And this would be displacement in 2 dimensions, right? So what we have is some reference frame A, keyword reference frame. This is where we are observing the physical phenomena from. We have a reference frame at A and one at B, and they could both be moving at different speeds. Right now we're looking at position, and what we can do is say we can locate position B from A. We can also locate position, let's get a different color, the location of P, and we can also locate all the way from A, the location of P. Let's give them some names. So this would be the X location of P with respect to A. And if you notice, that actually equals this one plus this one. And let's call this one the position of P with respect to B. And then this would be the position of B with respect to A. So we can say that the position of P with respect to A is just both of those vectors added up, right? And that would give us X of B with respect to A plus X of P with respect to B. I'll rewrite that a little bit bigger because we're going to hold on to that one. Plus X of P with respect to B. Alright, so if we have, we can basically locate any point in a moving reference frame as long as we know what location of one of the reference frames is with respect to where we are, and wherever the position of the object of interest, in this case the vehicle that was moving, as long as we know how far it is from the moving reference frame, B. And they can both be moving, so don't think that A has to be at rest. It does not. Okay. So check this out. We can take the time derivatives. If you don't expect the time derivative or integral by now, you're not paying attention. Just kidding. If we take a time derivative of this, we are going to get the velocity of P with respect to A is equal to the velocity of B with respect to A plus the velocity of P with respect to B. Let's make sense of this one real quick. So let's say you're at a stoplight and you're in your car. This is you in your car. Let's call it A. If someone passes you and you're at rest, so we'll say velocity of A is equal to 0. If someone comes along in another car, has some velocity vector, we'll call it B. As it trucks along, let's give it a number, let's say 20 meters per second. We can say the velocity of B with respect to A is equal to the velocity of B minus the velocity of A. And check it out, I can rearrange this equation. Oh, that's supposed to be a V. I can rearrange this equation to say just that. I can say the velocity of P with respect to B is equal to this one minus this one. The velocity of P with respect to A minus the velocity of B with respect to A. So what is it? How fast is that car going with respect to you then? It's going 20 meters per second because we have the velocity of B minus 0 is equal to 20 meters per second. Let's do another case though. What if you were actually going 15 meters per second? You're no longer at rest, and someone is moving past you at the velocity of 20 meters per second still. Well, the velocity of B with respect to A in this case would be equal to that 20 meters per second minus the 15 meters per second. So it appears, well, they are actually going 5 meters per second faster than you, but even though they're going 20 meters per second, they only appear to be going 5 meters per second faster. Okay, now we take it one step further and say, what if someone is standing out here and watching y'all? Well, you are one of these reference frames now. The velocity of, you have B moving with some velocity, you have A moving with some velocity, and we can analyze the motion of one of those knowing the other. How can I say this? If I wanted to know the velocity, so if this, let's change these subscripts so that we have ones that match this. This would be our point P, this would be our point A, or sorry, our point B, and this would be our point A. So we would get, if I wanted the velocity of the car, this one right here, P with respect to A, well, let's say I knew the velocity of A, and of B with respect to A, and P with respect to A. Velocity of P with respect to A. The velocity of, I'm just copying it down real quick, and then we're going to substitute P with respect to B. So P with respect to A, this was, in this case, a 20 meters per second, because that was with respect to the ground, and this person over here is at rest. B with respect to A ended up being a 15 meters per second, because they're measured against the ground also. So we can figure out what the velocity of P with respect to B is now. Or if we had this, we could find this, vice versa. If you know 2, you can find the third. So the velocity of P with respect to B in this case would be what we found earlier, 20 meters per second minus 15 meters per second. Gives us a 5 meters per second. It feels like they're passing us at 5 meters per second faster. Okay, one more trick would be to take the derivative of this equation. Let me go ahead and rewrite it. The velocity of P with respect to A is equal to the velocity of B with respect to A plus the velocity of P with respect to B. If I take the time derivative, we have to note that the velocity of B with respect to A is actually constant. This ends up giving us an acceleration of P with respect to A being only equal to the acceleration of P with respect to B. So this has to do with inertial reference frames, and I'll go over this some more, but basically, and there's a little star in your book with a little blue box. I really recommend you digest this box as much as possible. It's only one sentence, but I guess I can write it. Observers on different frames of reference that move at constant velocity relative to each other will measure the same acceleration for that moving particle. So in this case, the same acceleration for p, right? So this is that blue box. Make sure you understand that. Basically, if we're measuring the acceleration from A of p right here, it's going to be equal to the acceleration of p with respect to b. That might take 2 dimensions to help understand this, or maybe actually work in some problems. Read too. Also, make sure you read 4.6 and 4-7. So let's go ahead and talk about 4-7. It's just the same thing in 2 dimensions now. So to do that, let me draw a couple reference frames. And we'll call this frame A, this called frame B, and we're looking at X and Y coordinates. And we have some particle P out here. This particle could have a velocity, it could be moving in any which way. But what we want to know is how can we locate it, how can we find its velocities and relate its accelerations. So let's start with position. Notice we can go ahead and draw a vector locating B from A. So that's a position vector R of B with respect to A. I can also go from either one of these and say that this would be the position vector of point P with respect to A, and this would be the position vector of point P with respect to B. Don't forget your vectors. We could say that frame B has a constant 2-dimensional velocity relative to frame A. So let's just say that there's some velocity of B with respect to A. We typically wouldn't have 2 reference frames if they're both moving at the same velocity. So frame A typically, can't write, the velocity of A is typically not equal to the velocity of B. We wouldn't be using this. Now, what we can see is that this position vector is actually equal to these 2 things added up. And your book is going to write this as the position of P with respect to A is equal to the vector sum of R of P with respect to B plus R of B with respect to A. Need to know that one. We also need to take the time derivative of this and get the vector form that we just saw. The velocity of P with respect to A is equal to the velocity of P with respect to B plus the velocity of B with respect to A. And once again, for one-dimensional, because the velocity of B with respect to A is constant, when we take the derivative, that's going to go away, and we just get these 2 terms right here. We get an acceleration of P with respect to A. It's going to be equal to the acceleration of P with respect to B. So each observer, once again, sees the same acceleration. Okay, probably come back and do an example problem.